Scientists spent more than a decade designing and preparing this telescope. Years of engineering, testing, delays, and careful planning all led to one extraordinary moment. In July 2023, the European Space Agency's Euclid spacecraft finally launched into space. But Euclid was built for something far bigger than taking beautiful pictures. Its mission is to investigate two of the greatest mysteries in modern cosmology: dark matter and dark energy. Together, these invisible components are thought to account for roughly 95% of the universe's total energy and matter content. We cannot see them directly, yet their influence is written across the structure and expansion of the cosmos. Almost everything visible to us, the stars, planets, galaxies, and glowing clouds of gas, represents only a small fraction of what the universe contains. Dark matter does not shine, but its gravity helps shape galaxies and the enormous cosmic web surrounding them. Dark energy, meanwhile, is associated with the accelerated expansion of the universe. That is why Euclid was built. In March 2025, ESA released the mission's first major survey data, revealing an enormous collection of galaxies and providing an early glimpse of the vast cosmic structures Euclid is designed to map. The release covered about 63 square degrees of sky and included observations of millions of galaxies, with some lying more than 10 billion light-years away. And this was only a tiny preview of the mission's eventual survey. Euclid is expected to map roughly 1/3 of the entire sky and study billions of galaxies by the time its main survey is completed. Instead of simply looking at individual objects, the telescope is trying to understand how galaxies are distributed across space and how that distribution has changed over billions of years. One of the most important structures in that story is the cosmic web. On the largest scales, galaxies are not scattered randomly. They form enormous filaments and sheets surrounding vast regions of emptiness. These structures developed under the influence of gravity, with dark matter acting as an invisible framework that helped ordinary matter gather into galaxies and clusters. Euclid cannot photograph dark matter itself. Instead, it can detect its gravitational fingerprints. One of the most powerful techniques it uses is called weak gravitational lensing. Massive structures distort the apparent shapes of more distant galaxies because gravity bends the path of light. By measuring those incredibly subtle distortions across huge areas of sky, scientists can reconstruct the distribution of invisible mass. In other words, Euclid is attempting to create a map of something we cannot actually see. The mission has already demonstrated how powerful its instruments can be. During its early observations, Euclid captured an extraordinary gravitational lens in the galaxy NGC 6505. The alignment between the foreground galaxy and a much more distant background galaxy produced an almost complete Einstein ring, a luminous circle created when gravity bends distant light around a massive object. NGC 6505 itself is about 590 million light-years away. Astronomers had known about the galaxy for more than a century, but Euclid's sharp imaging revealed the hidden lensing structure with remarkable clarity. And Einstein rings are more than just beautiful. They allow astronomers to study how mass is distributed around galaxies. When the amount of gravitational influence exceeds what visible stars and gas can explain, dark matter becomes an important part of the picture. Across its full survey, Euclid is expected to discover tens of thousands of strong gravitational lenses and generate an enormous catalog of weaker lensing signals. Each one provides another piece of evidence about how matter is distributed throughout the universe. Then there is another remarkable part of Euclid's mission, our own Milky Way. In 2025, the telescope observed a huge region toward the inner Milky Way, creating a mosaic containing tens of millions of stars. Euclid's enormous field of view allows it to capture huge areas of sky while maintaining sharp images from space. This matters because the crowded center of our galaxy is also an excellent hunting ground for microlensing events. Microlensing happens when a foreground object passes almost directly in front of a more distant star. The gravity of the foreground object temporarily magnifies the background star. If a planet is orbiting the foreground object, it can produce a tiny additional distortion in the brightness pattern. That makes microlensing especially useful for detecting planets that would otherwise be extremely difficult to see. It can even reveal rogue planets, worlds that no longer orbit a star. These objects may have been thrown out of their original planetary systems and now travel through the galaxy alone. They emit little or no visible light, making them extraordinarily difficult to detect directly. But when one passes in front of a background star, its gravity can briefly reveal its presence. Euclid's observations will help astronomers search for these mysterious free-floating worlds and other faint objects such as brown dwarfs. The telescope is also helping scientists study galaxies that are almost invisible. In galaxy clusters, some enormous structures contain relatively few stars and therefore appear extremely faint. Their diffuse light can be difficult to detect with conventional observations, but combining data from space and ground-based observatories can reveal clues about their true nature. These observations are important because galaxies do not all evolve in the same way. Some are smooth and elliptical. Others form dramatic spiral patterns. Their shapes are influenced by mergers, star formation, gas, environment, and the distribution of dark matter around them. Euclid's enormous galaxy catalog allows researchers to study these shapes statistically across vast distances and different periods of cosmic history. That brings us to perhaps the biggest question of all: dark energy. For decades, the standard cosmological model has treated dark energy as something resembling a cosmological constant, a component whose density remains constant as the universe expands. But observations from the Dark Energy Spectroscopic Instrument, or DESI, have produced intriguing hints that dark energy might behave differently. DESI's measurements of millions of galaxies and quasars have been used to reconstruct how the expansion of the universe changed over time. Some analyses have found evidence that dark energy may have evolved rather than remaining perfectly constant. That would be a major development. But it is important not to overstate what the data currently proves. The evidence is intriguing, not a confirmed replacement for the standard cosmological model. More observations are needed to determine whether the apparent signal is a genuine property of dark energy or the result of statistical effects, systematic uncertainties, or something else. And this is exactly where Euclid becomes extremely important. By combining enormous galaxy maps with weak lensing measurements and other cosmological observations, Euclid can provide an independent and powerful test of how the universe expanded and how cosmic structures grew. If dark energy truly changes with time, Euclid should help reveal that evolution. If it does not, Euclid will provide some of the strongest constraints yet on the standard model. Either outcome would be important. The mission is also studying the universe on much smaller scales. Euclid has observed enormous clouds of gas and dust where stars are forming, allowing astronomers to investigate both the nearby universe and distant galaxies within the same mission. It is also revealing rare galaxy structures that may contain clues about the growth of supermassive black holes. When galaxies collide and merge, their central black holes can eventually form binary systems. Over enormous periods of time, those black holes may spiral toward one another and ultimately merge, producing powerful gravitational waves. By identifying galaxies at different stages of this process, Euclid can help astronomers understand how galaxies and their central black holes evolved together. And all of this is happening while other observatories are looking at the universe from completely different perspectives. The James Webb Space Telescope is examining some of the earliest galaxies and stars ever observed. DESI is measuring the positions and redshifts of enormous numbers of galaxies. Other ground and space-based observatories are measuring the cosmic microwave background, supernovae, gravitational waves, and distant galaxies. Together, these projects are putting the Standard Model of cosmology through one of the most demanding tests in its history. There are already several tensions in cosmology. Measurements of the universe's expansion rate do not perfectly agree. The behavior of dark energy remains an open question. The distribution of matter on certain scales continues to challenge researchers. And observations of the early universe are revealing structures that force scientists to examine how quickly galaxies and black holes could have formed. None of this means that modern cosmology has collapsed. Science rarely changes because of one strange observation. Instead, researchers gather more data, test competing explanations, improve measurements, and see whether the same pattern survives. That is what makes Euclid so important. Its ultimate goal is to build an enormous three-dimensional map of the universe, covering thousands of square degrees and billions of galaxies across billions of years of cosmic history. By measuring galaxy positions, shapes, distances, clustering, and gravitational distortions, scientists can investigate how the invisible structure of the universe evolved. The mission is still in its early stages. The first major release was only a fraction of the observations Euclid is expected to collect over its mission lifetime. Much more data remains to be analyzed, and future releases will provide increasingly detailed views of the cosmic web. That means the discoveries we have already seen may be only the beginning.